Griffiths section 2.3.4, the potential from a localized charge distribution. Last time we introduced the electric potential V, and we showed that the electric potential was related to our electric field. It is the electric field being the negative of the gradient of my electric potential. So if I think about some spatially varying electric potential, I can imagine I have regions of positive charge that generate some high values of potential, and some regions of low potential that have negative charge. And because this is the gradient, that means that the electric field points in the steepest change of my electric potential. It points down that hill because it's the negative sign. Okay. So there's this relationship between the charge, or I guess rather I should say Q, the charge distribution, the electric field, and the potential. And you've already established that there's a way to go from the charge to the electric field and back and forth. Last video we showed that there's a way to convert back and forth between the potential and the electric field, either via an integral or taking the gradient. And what we're going to do today is show that, or in this video, that there's a way to connect between the charges and the electric potential itself. So you have a number of different strategies given the context of the problem. So let's go ahead and put a point particle of charge Q at my origin. I want to know what is the potential at some point P. Since I'm at my origin, I can call that a really regular vector R. And I know what the electric field is from this point particle. So I'm going to take advantage of the fact that if I integrate over some path, I can figure out what the potential is. So the electric potential at some point in space R is going to be equal to negative the integral from some reference position to that point of E dot dl. Let's take the easiest possible path, dl, which is just a straight line along the dr direction. That becomes minus 1 over 4 pi epsilon naught infinity, that's what I'm going to set as my reference point, r q r prime squared dr prime. All right, r prime being the where the charge exists. Okay, I can, so rather, it's not where the charge exists, it's just to differentiate between this. Okay, so I can solve that integral, and that gives me that the electric potential at some point in space R is 1 over 4 pi epsilon naught Q over R. All right, so it looks very similar to the electric field. And if I wasn't at the origin, I could in general write the electric potential at some point in space being 1 over 4 pi epsilon naught Q over script R for a point particle. All right. But the electric fields and the potentials can all be can all be generated for a series of point particles. Right? I just add up the individual contributions of each of those. So I could write for an assembly of point particles, I could write the electric potential at some point in space being 1 over 4 pi epsilon naught, and then that's just the sum over all of those points, qi over ri. Okay. Or if you wanted to say that instead of being a series of discrete points, you had a continuous distribution, you could just rewrite that sum as an integral. integral then becomes over dq over r. And there are a number of different ways that we could write that. So let's assume that we have a volume charge distribution. We could write the electric field, or the electric potential, as being 1 over 4 pi epsilon naught integral over that distribution where the charges exist. Now the primes are related to the locations of the charges. If I had a surface with some charge distribution, I could write the electric potential as being 1 over 4 pi epsilon naught integrating over that charge distribution. Or if I had a line charge, I could write what that is. But all I'm going to do is I have to change the type of charge distribution and the infinitesimal volume, area, or line element to match the appropriate condition.